Hi everybody, thanks for coming. My name is Corneliu Hoffman. So I will start by lowering expectation as usual, right? You should do that before a talk always. So I don't think I prepared this well enough. It was all, we had some issue at work, but anyway. So hopefully, I don't like my slides. They came up a bit formal, so I'll talk about through them. So I work for a cybersecurity company called Aikido. In particular, I am one of the maintainers of an open source static checking and security product called OpenGrep. We are OCaml shop that basically what it does is, what the product does is sort of takes a code base in whatever language you have, transforms it into a generic AST, and then allows you to grep it in a more coherent way than just text. And you can find things that you can find various vulnerabilities in your code by traversing this AST. So I'm just putting this into context because my choice of paper is somehow connected to some things I've been reading about in order to deal with some issues within OpenGrep, and you'll see that in a second. It's the paper that I listed there is about webs, but I will talk about zippers a lot. If I get to webs, fine. If not, it's all right. This is going to be a very unapologetically functional talk. So if you're very object-oriented, you're going to shout at me because all of this is trivial in object-oriented languages. It's also very unapologetically statically typed. So again, Clojure folks, I have a slide where I say this is all trivial in Clojure, but anyway, bear with me. So the idea is, why do I care? So basically in OpenGrep, we have these big trees which represent a program in a language. They basically are some sort of union of all possible syntaxes of all possible languages we cover with intersections, right? I mean, an if, it's an if regardless of the language, and so on. So we need to do pattern matching across code. We need to traverse this to see that, okay, well, if I have the secret in this place, does it traverse through this code and gets read somewhere else by a print? And things like that. We need to, which is what we call taint flows, and we need to transform codes every now and then. Not a lot, but we'd like to be able to do things like that. At least, if not transform it, access things which are deep in this tree. And so we'd like to keep track of this current position, and we'd like to move up and down, and perhaps also edit stuff that propagates up the chain. So and also maintain type safety, whatever that means. In the context of the AST is very strongly statically typed, so we like to keep that, and we will see why the initial story, the zipper, is not that good about this. So let's compute. I mean, I picked that directly from the paper. So simple kind of AST, you've got some variable, you've got some a let, and then you've got some application of a function, and then you've got an if. It's not so relevant. I mean, you can't write very many programs with this. It's just there to see that you might run into problems with this. So, for example, if you have the right-hand side of a factorial, again picked out directly from the paper, but instead, so I mean, you can understand what this is happening. It's a function of n, and then if n equals 0, you get 1. Otherwise, and there's a problem here. It's instead of multiplication, you have an addition. And how do you fix this? I mean, it's, if you didn't have an editor, but you wanted to somehow look at this AST and fix it, how would you do it? right? So how do I change the plus into a star? And, you know, of course, I can just say, look, I've walked left, right, and remember myself, and, you know, somehow just have this list of paths and things like that. It's very ad hoc, and it requires going through all kinds of things, slow, and then you need to rebuild, and so on. And, you know, you could have some sort of pointers, which I'm not going to talk about because I said it's unapologetically functional. And there's circular references because it's recursive and so on. So this is the first thing I want to talk about, and I'm going to spend quite a bit of time here. So there's an old paper. I mean, all of this is old, so 2001, I think the paper is. So I'm going to keep us fresh from the fact that the AI is taking over our lives, so there's not going to be any AI here. So old paper, 1997, the zipper. It's a lovely paper. If you have not read it, go ahead and do. And then there's a follow-up paper that I'm going to talk about, I'm going to list at the end, which brings in some of this story. So the idea is that you need to think about a data structure as kind of a sweater with a zipper. So walking inside of a data structure is as if you unzip the zipper, and then you can zip it back up. And then you have this stuff, you have the current focus, you have a context, which is kind of a structure with a hole that tells you where you are. And maybe you have the term that sits at that hole. And so the context is, I've walked in this structure for a while, and I've arrived here, and that's what's there. And if I want to change it, I just change that guy and zip back up, right? So sort of that's in brief. I'll have some examples. And so then you have moving, which is zipping and unzipping, so you can move down, up. So you can have things like that. You have a term, and then you have a context, which is exactly this context with the hole, and you can go back up and so on, and you have a top and so on. So let me stop here for a second, and the next two slides, I think that's all I have. Yeah, the next two slides are going to be examples, right? And the first example used to be one of my favorite sort of interview question. So how do you change? You have a list, a functional list rather than an array, and how do you change some value inside that list, right? How do you do that without actually being too horrible, right? So what do you do about it? So the only thing, as with any functional list, the only thing you can do is you can take the head and the tail. That's it, right? And you do that for a while, but then what do you do? And if you think about it for a little bit, sorry. This is what a list, well, actually, let me not show that first. Yes. So a list is something that has a head and a tail, which is also a list, so recursively defined, right? And what you do is you basically have two lists, right? Whenever you take the head, you put it in this other list, and you keep doing it till you arrive, 7 times, say. Right? At this point, you have two lists, one which is this context, so to speak, and the rest of the list. You change the guy, and then you unzip, you put them back. Because remember, you put them at the beginning, so this is in reverse order, so it's perfectly fine to unzip it. Right? So shoes and socks kind of thing, right? You take your shoe from this one, you put it here, the sock on top of it, and then when you undo it, it's perfectly fine, right? So that's this is the point of a zipper. You have a context, which is the left. I mean, in this case, the context turns out to be also a list, but in reverse order. It's not really a list, it's a context, right? And then you have, the rest of it, which is the rest of the list, and then you have the value, which is at that point, right? And you have a way of going forward by just keep putting things into this list to the left-hand side and so on, and you have a way of unzipping. There are more complicated things, and I'll have another example here, but I'd like to, so this is the example that I was talking about. This doesn't quite make sense, but if you think about it, It does, right? So it will make more sense as we talk about it, but what does this mean? A plus is like an OR, it's like a sum type, right? So it's either a 1, which is the empty list, or a pair of whatever x is, whatever the type of x is, and another list of x, right? That's some sort of abstract definition of a list, right? That's abstract recursive definition of a list. Whatever that means, it'll make a bit more sense in my examples later. This is what I was talking about. You have the left context, and you have the right context, and you've got the guy, the 2, which is in the middle, right? And, you have the left list before focus and the right list, which is after focus, right? I want to talk about the next example. Oh, sorry, and the context is a pair of lists, yeah? The more general case, it's a tree, right? The rose tree, people call it, right? The proper tree, which has, at every point, at every node, it has a value, and it has a bunch of children, right? So nodes with a value of type X, and a bunch of children, which are also trees, right? And this is the general story. This is kind of a picture, right? And what do you think a context of a zipper would be? Let's think about it. Say I walked to D, right? The idea of this would be at every step, right? I will have, so basically I'll have a path to this tree, to D, and then I'll have, maybe I walked, so if I arrive at D, I'll have the left siblings of D and the right siblings of D. Things which are before D, and there's none here, but, sorry for the mix-up here, but the right siblings of D are just E. Right, so basically you have a path to the vertex, and then who's to the left and who's to the right of D. Right, and that's basically what the context with the whole is. So if I now want to change D, right? D will be a 3, kind of thing. Maybe it has some children as well, and so on. But I will change the D and then unzip it because I know the path. Right? I'll be a bit more formal in just a second, but I want to show you that picture, and I really like this. The next couple of slides are very, very cute. So think about lists as power series. So remember the formula, right? List is 1 plus x times list, right? That's the story. Yeah, if you do just normal arithmetic, just move this to the left-hand side. Yeah, so you'll have list of x times 1 minus x. You divide by 1 by 1 minus x. You get list is 1 over 1 minus x. And if you expand this in power series, that's what it is, right? But you knew that, right? That's what the list is. It's empty, or maybe with 1 element, with 2 elements, 3 elements, and so on, right? That's what a list is. And it's basically the coefficient of xn is, it's not really the list. So basically, there's one kind of list with n elements, right? Now let's go further with rose trees. Rose trees are a little bit funkier, right? They are node and a list of trees, right? So list of 3 of x. 3 of x is list of 3 of x, right? But then, I know what list of 3 of x is this. It's 1 over 1 minus 3 of x. Yeah? So if I put, instead of this, I put 1 over 1 minus 3 of x, and cross multiply, I guess 3 of x minus 3 of x squared equals x. Right? This is an equation of one variable. It's a function that's defined by that equation recursively. If you do a little bit of calculus, you'll get, keep doing like Taylor series and such, take derivatives as 0 and so on. You get this, 3 of x is this. Yeah, these are the so-called Catalan numbers. It will tell you, the coefficient of x to the n will tell you how many shapes of a tree with n nodes there are. Shapes in the sense of sort of leveled tree. So like there's one tree with one node, very hard. One tree with 2 nodes, Yeah. Then there's 2 trees with 3 nodes. One is a and the other one is a line. And then you keep going, right? There's 5 trees with 4 nodes and so on. Right? So a little bit of kind of silly calculus. This is standard kind of combinatorial generating function stuff, right? Which you would see in any kind of combinatorics, fancier combinatorics class. Next stuff isn't. So there's a surprising connection between zippers and just formal derivatives. So zippers basically relate to derivatives. And you have this type algebra that I just said, right? If you have a sum type, either A or B, then you call it A plus B. And you have a product type, which is, if you have a product of A and B, then it's just A times B. So a pair of A, B will be A times B. Whatever A and B, whatever types A and B have, right? And then you have some recursive types. I'm not going to talk about that too much. And now I'm saying that the context with a whole of one of those recursive types, it's going to be the derivative of this with respect to that type. And let's try to see that this is the case. So I'm saying this is not just notation. This is actually the type. It works. And I'll hopefully convince you with these 2 examples. It's like physics, right? I've had 2 examples. That's it. This is a proof. So we have the normal product rule, the derivative of a product. It's, and that means that if I have a pair, then the whole, it's either in the first one or in the second part. That's how you interpret the product rule. I'm getting to, this is basically a sketch of the proof. Product rule corresponds to the fact that if I have a pair of types and I want to interpret this as being a zipper, well, it's not a very deep zipper. It's either you've got a hole in the first place or the hole in the other. And of course, the sum rule, it's, well, if I have an or, it's the sum of the 2, right? And you have derivatives, your distributes of a sum. So let's look at the list to convince you of the first thing. So, well, a list of x, as we discussed, it looks like that. I'm going to take the derivative of this. Well, there's nothing. 1 is 0. And then you take the product rule. So it's 1, because the derivative of x times list of x, plus x times, list of x, yeah? So x times the derivative of list of x. So you see, the derivative of list of x, it's equal list of x times the derivative of list of x, right? And so I can move everything to the left-hand side, this thing to the left-hand side, and I will have basically I get list of x times 1 minus x equals with list of x, right? And so I divide by 1 minus x, the derivative of list of x, it's list of x over 1 minus x. But 1 over 1 minus x was list of x. And so the derivative of list of x, it's a pair of lists. Just like the zipper of a list was a pair of lists. Right? Just completely stupid calculus, 101 calculation tells you this is what you expect from the type of the context of a zipper of a list. This stupid calculation. Yeah, go on.
So you said earlier that the zipper is the first list is reversed.
Yeah, that's what I was going to say. I was going to say that this stupid calculation obviously is not going to tell you how to do it. It's just going to say that whatever this context looks like, it's going to be a pair of lists. It's not going to interpret the 2 lists for you. It's just going to say, look, this is, figure it out. Whatever you get, you better looks like a pair of lists, no more than that. I mean, that's that's why AI is not going to yet take our jobs. You have to figure it out. Let's look at the rows tree again. Okay, the rows tree looks like x times list of 3 of x, right? Take the derivative of that. It's, list of 3 of x, and then this. right? So again, you know, you do this one, you need to use the chain rule, right? So it's the derivative of list of x times the derivative of t over x, right? And the derivative of t of x, we already know it's list of t squared, right? We've done that before. It's a pair of lists. And so here is my story. The derivative of a 3, so meaning the context of the 3, looks like what? There's a list of 3s, and then some beastly thing that looks like that. Okay, I'm not going to do any more fancy arithmetic on it. That's it. That's all we know. But we're going to think about it a little bit and try to figure out what it means, right? And what do you think it means? Okay, list of 3. This is when you arrive at the node, you need to know the children. So it's either you're at the node and you have the children, or you walked for a while and then you have a node and a pair of lists, which is left siblings and right siblings. Right? So if we go back to this, let's see if I can. Here. If we go back to this story, what does it say? Okay, what would the context look like? It's either that I'm here and I have these 2 children, which are 3s, or that I walk for a while, which is a recursive d of this 3. I walk for a while, and then I've arrived to this place, right? And then this guy is going to be another stuff, like maybe it's children, and then it's going to have left siblings and right siblings. Right? And you know, homework, try it for a binary tree. It's easier. But so harder than list, easier than this. It works for whatever structure you want. The idea is that the context of a tree, it's the context with a whole, not a tree, of some sort of recursive structure, it's going to be the derivative of that structure. Whatever that means, right? I mean, it's this, you know, again, type theory, as statically as it is not going to solve your problem. The fact that you know the type of a function doesn't mean you know how to write it, right? I mean, it just tells you that you can't write it very wrong, but you could still write it wrong, right? I mean, you could still reverse the first list and put them back. I mean, that's it's a function that perfectly type checks. It's just a silly one, right? Or you could just throw away the left-hand side. I don't know. Yeah? Sorry. All right. So again, either you're at the first step and you have list of lists, or you have a path, left siblings, right siblings. Yeah? So the core idea is that you go back up. I don't want to spend too much on this story, but I'm going to tell you what my problem is in my kind of statically type AST. My AST is very, very recursive. It has all kinds of things. It has terms, it has expressions. The expression could be an assignment, it could be a call function, it could be all kinds of things. I've only given you 3 things, and this is what I need in order to build the tree. I've already made it into 7 things. I need to know what to do with this one, where this is a context. I need to know what to do with this one, where the context is here. I need to know what to do with this one, where the context is here, and so on, right? So just a simple thing, I need to construct this horrible thing. If I have a thing, in the generic AST of Open Grep has, I don't know, 200 types, something like that. So you don't want to do that. You don't want to write this. And Renzo's looking at me like this because you're a closure guy. You don't care, right? So here's my So you know, if you're dynamically type, you don't care. It's got a child, I'll work to this child, that's fine. You know, it's gonna, you know, if I have a problem, you know, when I run it, they will tell me, right? So no type checking, so context could be any, I don't care. And you know, you keep track at runtime, and you have one zipper. It's actually part of the standard library, the zipper, right? You don't even have to make it, it's there. So it's, you don't have compile type guarantee. It's a bit expensive because of this, but and then you have some type errors. In things like OCaml or Haskell or, you know, other things, type safety is a feature, but it costs. Because you need to know what the context is. You can't just say, I'm just going to look at the child of this. And somebody's going to ask, well, what's the child type? And you have to go, well, the child type of this is recursive, and he uses the child type of this guy. And so it's a little bit of a problem, right? So you need to write a specific zipper for every single term type. You need to write a context there, and the thing explodes, and it's kind of untrackable. There's a lot of boilerplate. And I just don't know how to do it like that, right? So not reusable, as I said, small term type, 7 possible context constructors. And you start with another AST, you don't have a box. So you don't have a zipper in the thing. You have to make it yourself. So can we do it better? And OCaml has this really cool thing which annoys me to no end because of this O here. OCaml has this PPX. You know, in OCaml there are these sort of standard macros which are built in, so which sort of write code for you. So there's a standard macro called visitor. So essentially, if I give you a very complicated tree with recursive things and so on, you just write there implement visitor or derive visitor, and out of the box come at compile time, not at runtime, but at compile time, or out of the box comes like a completely typed, unreadable thing. But the plus is you don't care what it looks like, because it's going to have something like, so you have visit abs, which is a function that deals with, it's already built. It doesn't do anything. It just takes that guy, gives it back to you, and keeps going. And so it builds this horrible thing for you, and then when you want to use it to do something, you just modify it's an object, so you modify the method for that object. If you want to say, I want to count how many abs I have in this story, well, you feed these functions with some sort of counter, and every time you see an ab, you add one to the counter and then keep going. It works. We use that a lot in OpenGrep, but I really hate it because it should just be camel. You should not program with object-oriented things in a language like OCaml. But it works, and it's effective, and it's fast, and, you know, type safe and everything. But I don't like it. So I've been looking a lot. So there's inheritance and open recursion and all kinds of things, and there's separation of concerns. It's kind of a nice thing. I've just been searching for, this is my sort of, every time I look at the code, I go, can I kill this? And I just didn't find yet a good way to kill it. And I've been looking at, and this is where this idea of you know, this is where the rest of the paper comes in. And the idea is, you know, again, has some problems. It's a kind of a one-way transaction, right? I'm walking through this. I have a language that has classes, right? And classes have methods. And I somehow have this visitor, and I've arrived at the method. And I want to know something about this method, but it's not just a method, it's a method of a class. If I did not remember to put that class in my, whatever I did that, then I wouldn't know. Because I can't go back and say, well, what class did you have? Right? That's the one-way traversal thing. Yeah, you know, you have to keep remembering, if I need to know some ancestors of this guy, I better put it in something, some sort of context, right? Which is a bit annoying. You know, again, there's no focus. You can't just say, well, where are you? Because it's kind of, you're blind to it. You just apply to it, you apply it, it's like one of those machineries, right? With a zipper, you can work in a repo, right? I've made a step in the zipper. What happened? I made another one. What happened? Let's go back. Let's go to the left. That's kind of effective. With this one, you can't. It's like one of those, you know, you put it there and it works for you. But then if you have a bug, what was it? You can't. It's also not working very well with the LSP. So you can't go through the methods. It's a pain. And so you can't go to the left, you can't go to the right, you need to have a state, and you cannot edit at all. You don't, that's not what these things are for. And still, there's a little bit, still one visitor per AST and so on. You don't do that, the machine does it for you, the PPX does it for you, but it's still there, still knowing at the back of my head, I've got this 400 methods, 400 lines of methods somewhere. If I was to print whatever happened in this thing at compile time, if I was to print the compile code of whatever we had, there's probably 20 visitors in this. So that's like thousands and thousands of methods. That's unfair. Right? It's not human. So again, zipper limitation, there's type specific, there's a lot of boilerplate, and for large AST it's not there, neither here nor there, except for in dynamic languages. Or, I mean, again, once again, if you live in an OOP world, yeah, this is not the problem. You have pointers all over the place, so you know how to change things. You change the thing it points to. So this is the part of the thing which I didn't spend enough time to make it very careful. So hopefully it will make sense. So the idea is that just like a zipper, it's kind of just like the zipper, it's the context with the hole, it's a zipper, it's the derivative of the type. It's kind of like a tangent line to the type. It tells you which way to go and which way you're coming from. It's like a direction. This idea is like kind of the set of all zippers all together. So it's a machinery that is supposed to say, well, you know, I have this type, and so the thing they did is that they produced these guys, con0, con1, con2, and so on. So again, it's not perfect, and I don't think I'll use this, but I thought it was a cool thing, so I'll tell you about it. So the point is, they built a library in Haskell that builds these things. I think. I actually have no idea how far it goes, because you can't have, Haskell is not dependently typed, so you can't just say con will be a function of n, where the type of the result is going to depend on n. So I think they built 20 or so these, just step by step, because that's, you assume that you're not going to have. I mean, it's unreasonable to say, I'm going to have a type which has 40 types of children. You can have 1 million children, but they better be of fewer types. It shouldn't be like this guy and this guy and this guy. They're all different types. So this is just saying, I have these kind of concatenators, if you say, the combinators, but they sort of, in order to define the weave, so you're saying I'm weaving a web, that's what they're doing. So the weave takes a term in my world and transforms it into a term weaver, which I will tell you what it is in a second. And it's a function that takes the variable, it's a recursive function, and you see these. So the idea is that you kind of have these automatic almost automatic. You only need to build this. So basically, this is a, kind of a linear thing. You just build that for every type you have in the term. So much less than the other. And then once you have that, so the weaver looks like that. It's taking a way of a lock, it's much like the position in the zipper. We'll see what a lock is in some examples, but it's like a location for the zipper. So you have a function that's kind of a weaving function that takes a term and creates a location for that kind of term, and then if you have one of those functions, you get the location. So in other words, it's like giving a parent link function, then you build a location. So basically a weaver, it's an instruction for building location from functions like that. And this is the parent link function. And then you take an updated child and you return the parent location. So, okay, why wrap it? Forget about that. So what are these? So these are generic functions which are provided by the library. They look like that. They take one of those functions. So this is the con 0. It takes one of those functions, take a term and creates a weaver. Con 1 takes one of those functions, takes a function that takes an A to A, an A. Con 2 takes one of those functions, takes a function of 2 variables, and the 2 variables, and so on. Con 3 takes a function of 3 variables and 3 variables, and so on. So the con n takes the weave function for recursion, a constructor function, which this is the rebuilds the node, and then the n children. Okay, why this? So, for example, for abs, you can write this, and I don't really like this thing. So basically, this function, kind of, in the abs, remember this is a string, it's not a recursive thing, but T1 is. So this is a closure over the recursive thing. So you need to do that. So, and then you rebuild the node when you change the children, when you change the S and T, you can then rebuild the node, and then you can navigate up, down, and so on. So, right. So this is so I think I would like to probably stop with this following two slides and then talk my way out of this. So this is the zipper, right? The zipper has a location that looks like that. It has a term, so it should really be term location, right? So it has a term, which is a type, and it has this context, whatever this is, right? Depending on if it's, for the list was a pair of 2 lists, for the tree was this complicated thing. This is the web, it's a bit funkier. It actually has a location that has a term, and then it has these functions that go up and down and so on. So basically, it should be lazy. I mean, I'm writing this in OCaml, and that's not lazy, so you should be lazy. But ideally, the idea is if you have a location, the location has some stuff at that location, and it has these functions that move up and down to this location. So basically, what you do, you basically, when you're at the location, you say, I want to edit this. So you change this, and then you walk to the parent. So basically, you apply this F up to whatever you change, and there's a new thing which has a different stuff, but it already has this guy, the new guy, as a child. So this is you should view this as a kind of, as I said, as a web with up, down, left. I mean, it's not really a web, more like a lattice, if you want. And as it's described sometimes as kind of you have 2 directions you can go, right? Up, down, or left, right, if you want. Rather than, I mean, obviously in a zipper, you can build these things up as well, right? They're just not kind of, they're harder to come by. So I think I want to stop here and give you, because we have Oh, that's how much I don't like the next slide. So you can have connections and so on, but come on. Oh, I went to the beginning. To have some time for questions and to... Right. So this is the paper that we were talking about, and these are the two interesting papers, the zipper, which is the one I mentioned, and this is it's a paper by, I think, Conor McBride, which is called The Derivative of a Regular Paper. There's an older paper from like 2010 by a bunch of people, Ghani and Ghani and all, let's say, which does this much more abstractly with, I don't know, monads and stuff. But let's not go there. So my idea is that maybe I can simplify a bit time propagation and understand this, sort of get rid of the bloody visitors, but I don't think it's quite there. So let me stop here, and questions? Went a bit fast.
Repeat the question, and if somebody asks a question, can you please repeat
yes.
it? So it gets to the point.
Go on. Yeah, go on.
So I'm not 100% sure about the web, but with my untyped mind, I'm just trying to understand, is there any advantage, or is there any sense in having a web in an untyped language, or is just because you have the types,
yeah,
you arrive at the concept of the web?
Yes, because the problem in an untyped language like Clojure is, right?
Repeat the question.
Yeah, sorry. Is there an advantage in an untyped language to have a web? I don't think so. Just like there isn't one there's not an advantage to having a zipper in a object-oriented language, right? It's because if you have a way of addressing the stuff, you just change that stuff. I mean, you don't need to rebuild your structure. The same thing is true in a language like Clojure, right? If you have this huge AST, you don't care what the structure of these things are, right? You just go to wherever you want to do, make a change, and unzip it back, right? You might run into problems because maybe your AST breaks because your types, you put a 3 there and you're supposed to be a string. That's another story, but it's not going to stop you from editing an AST, right? I mean, that's the whole idea of a Lisp, right? It's your code is your data is code, right? So it's not a problem to deal with ASTs in a Lisp, right? So I don't think that's why I properly quantified that beginning, that this is unapologetically both functional and strongly timed. Yep.
Small question first. So what are you doing? How it is like similar to the three-seater library?
So we use the three-seater library. So the three-seater library is just a parser,
yeah,
right? So essentially what it does is it takes the syntactic sugar that is your language and transforms it into some structured thing, right? It does not transform trees, and it's not functional three-seater, but we actually, so OpenGrep is, part of it is based on three-seater parsers, because three-seater parsers are a dime a dozen, basically. Every language has 2 of them. So you don't need to reinvent the wheel in parsing a language, right?
I see. And if I may, like,
Yeah, go ahead.
As far as I know, like programming languages, AST is not a good representation of what's going on, and to be able to actually understand what this code represents, you should have a graph structure.
So
you don't have to like connect terms that.
yeah. So of course, we don't.
Usually be very weird.
Yeah, so we don't compile this, so it doesn't have to be a perfect representation of the language. But you're right, yeah, you need to have a connection. You have to have a graph between, like if you have this function here and you have inside of it there's a call to another function, that's not going to be part of the AST, it'll be somewhere else. So you need to have that connection as well, and that's a separate problem. So we deal with that a little bit ad hoc at the moment, and on the long run, we're probably going to do some LSPs on it or something, because LSPs control these connections. Go on.
And are you using like LSIF or LSIP like tools to like analyze code connections?
No. We at this point we have our own representation of these languages. So we have a very strict AST, and then we can understand stuff from the AST to see the connections. It's a little bit ad hoc at this point. So if you see a call, you'll find it somewhere else. So it's a bit ad hoc. Yeah, I've only worked on this for 3 months. You'll be better in a while.
How does zipper or web relate to optics?
To?
Optics, like lenses and prisms and all that?
Yeah, so they're kind of parallel in some ways, right? So they're, if you want something like a lens, it's kind of it's a piece of the AST, right? So you have to have connections between them. So in other words, so what, I don't know how much people are familiar with the idea of a lens. So imagine you have a big tree or graph, or let's say a big tree. A lens will be a piece of that tree. Let's suppose you have, let's not talk trees and things like that. Let's suppose you have a record that's very complicated, right? It has 40 million fields. Some of these fields are records themselves, and they all have 40 million fields. And then these have things like that, right? And you want to, you know exactly what you want to do. You want to just say, give me this, in its simplest form, you'll go like in a language like Clojure or basically any language that has some sort of kind of threaded stuff. You go, let me say, give me a.x.y.z.w. Or let me change x.y.z.w. But suppose you can't do that in a functional language. You can't just say, well, I'm going to have this in a statically typed language. You can't just say, well, I'm going to have this, or it's very awkward to say it, right? You will, even in a language like Clojure, it would be awkward to say, if I have a deep thing, I want to change this one. Yeah, you can, but it's going to be rather verbose. So a lens is exactly that. It has this idea that you have this embedding or map between this kind of maybe simpler record and this other record, so that you have a way of actually, so there's a connection between them. So you start with a big object, you can get the small object. If you have a small object and a big object, you can reconstruct the big object with changing just the thing inside. So you don't have free reign on the tree. You can't just do whatever you have. You only have access to the lenses you've built. So if you build all the lenses, then you can do that, but then, that's a lot of lenses. Yeah. So they're, lenses are like views in a database, kind of. Go on.
So from the last academic issue, it feels like the context of the location of realize the location of things up, left, down, right. Is that by design or is it because?
Sorry, the left, right?
Up, down, left, right. It's like one location is only aware of the
Yes.
locations. Is that by design or is there any variation like store a little bit of this type of locations?
So the question, to repeat the question, sorry, I remember. So the question was whether this sort of just these four directions, whether it's by design or should you build. I think it's by design. I think the point is that they are looking at, they were looking at things like ASTs and things like trees generally, and therefore those are natural natural questions. I guess if you had something more complicated, maybe you can have more directions. I don't know. Haven't thought about it. Good question. Go on.
Regarding this formal identity, list of x equals 1 plus x squared plus so on. On the left-hand side, if list is a lazy list, it can be infinite.
Yes.
Yeah, on the right-hand side,
Well,
we consider finite list.
No, you don't. Not necessarily. It goes dot, dot, dot. It's 1 over 1 minus x.
So, plus dot, dot, dot means summing till infinity, including infinity.
Yeah, so it's as I said, it's 1 over 1 minus x.
Some recursion, yeah.
Yeah, that's the point. There is the lists are defined recursively, and therefore, by that silly little formula, it just says list of x is 1 over 1 minus x, which, because of, again, silly calculus, is 1 plus x squared plus...
All these structures, lists, and trees are
Potential.
lazy, can be...
Yes, absolutely, yeah. And I think often they should be lazy because they could be very big. But, yeah, depends on your language. In Clojure or Haskell, they are lazy by design. In OCaml, you have to do work. So, yeah.
My question was about dot, dot, dot.
Yeah, so dot, dot, dot means, 1 over 1 minus x does not look like 1 plus x squared. It means 1 plus x squared up to infinity.
Yeah, but up to infinity, including infinity.
Well, what does that mean, right? It just means it's an infinite series, right?
A round bracket or...
Well, but there is no infinity. Right? What's the power of infinity? There is no power, right? It's just a formal way of saying this is a power series. It goes up to, you know the joke with there's a good story about that connects to your question. There's this sort of astronomy question, right? Talk. And the guy talks about, the skies and so on. So this old lady raises the hand and says, what are you talking about? Everybody knows there's an elephant that holds the flat earth and he sits on a turtle. And then the guy says, but what does this turtle sit on? And the lady thinks a bit about it and says, oh, you're very clever. But everybody knows the turtle goes on. So that's what I'm saying. The list goes on. It doesn't stop at 1,000. It's just a formal sum.
that when children count,
Yeah.
1 plus 1 second plus 1/4 plus so on, we do not include infinity. But here we include infinity.
No, we don't. There is no x to the infinity. It's like my father makes more money than your father, right? That kind of, you play, oh no, he makes 1,000. 1,001. There is no x to the infinity. That's what it says, 1 plus x squared. It doesn't stop, but there is no number that says infinity, right? Just like you said, 1 plus 1, 2, 1/2 plus 1/3, that's 2. Yeah, but it's not really, is it? Not unless you go to infinity. Go on. Sorry.
One quick one. When you're talking about typed holes, I never got the intuition of what a typed hole is. Comparing the algebra things you had earlier, is it like kind of solving for a type?
Yeah, so basically, that's what I was talking about, Clojure versus a strongly typed language. The point is that in a strongly typed language, when you say list of x, you better know what x is, what type of x is. So it can't just be list of x. You can have abstract types and so on, but you should know what that is. You might not, but when I'm thinking about type hole, it means, okay, I've got these two lists, but then I have this hole, but the hole is not just a hole. it's a whole which has type the same as these two lists. And so, yeah, in some ways you can deduce that the whole has that type. But my problem with the AST is that this whole does not have a defined type. It might have a type string for this stuff, or might have a type that's very deep for this other stuff, and therefore I'm running into trouble. What type is this whole?
But then the whole has not all the different subtypes of that.
Yeah, exactly. So then I have to, I have to write, every time I have to figure out this whole has a type, so I have to deal with this type that has these two subtypes, but also this type that has these two subtypes, and these other two, and for each one of them I have to, so it just sort of multiplies very quickly. Sorry.
So zippers are used both in lazy and non-lazy languages.
Yes.
Sounds like this paper uses Haskell.
Yeah, so it's...
Have you found any obstacles to applying the same ideas in a lazy context?
Yes. It's not a very good idea to have it non-lazy, because that means you have to hold the entire world in your hand, right? You have to build it all up. So even if you do OCaml, you have to be lazy about it. And there's ways to be lazy, it's not free. But you can't, I mean, if you're not lazy, then all bets are off, because it means you have this whole entire story in your hand. You need to know what are all the possible paths that I will ever take, and there's a lot of them. So whatever you gain this way, you lose the other way. Yeah, good question, thanks.
You're done?
All right. Let's go get beers. Thank you.
Okay, you want to stay longer, stay longer. You all need to be here by collecting stuff. And you want to do the chat, us to the power.
Yeah.